Alright YouTube, today I'm talking about a situation that I see a lot of people run into, and that is trying to find the direction of the electric field as the result of multiple charges. So here I've laid out a couple of different charges, and we're going to solve for the magnitude and direction of the electric field right here at this point. Now the fact of the matter is, coming up with the magnitude of electric field at this point from each of these three charges is actually pretty simple. It's the direction that really causes people trouble. Now solving for the electric field at this point from each of these three individual charges is actually pretty simple. We simply apply the electric field equation to each charge individually. See, each charge produces an electric field right here at this point, and the total electric field is actually the sum of these three electric fields. See, the problem is, if you go ahead and just add together these three magnitudes of electric fields, you're going to get this problem wrong, even if you account for this negative in this electric field over here. And the issue is direction. See, at this point in physics, most people are used to the idea that a positive is in one direction, typically right, and negative would be in the other direction, left. The catch is, when we're talking about electric fields or electric forces, positives and negatives are not telling us left versus right. Positives and negatives are telling us attractive versus repulsive. See, this 1 coulomb charge is producing an electric field which is repulsive at this point right here. That is to say, if I was to stick a positive charge right here, that positive charge would be pushed away from this 1 coulomb charge. Or to show this as a vector, the electric field is to the right. Now this 2 coulomb charge is also producing a positive electric field, but realize that positive doesn't mean right or left. It means that that electric field is repulsive. Going back to our positive test charge here, if we stick a positive charge there, it's going to be pushed away from this positive 2 coulomb charge. Now this negative 3 coulomb charge produces an electric field which is negative, meaning a positive test charge here would be attracted to this negative 3 coulomb charge. Ultimately, that means the electric field at this point, due to this charge, is to the right. So now that we know the actual direction of each of these electric fields, now we can go back to summating the three different electric fields. And in adding up the three electric fields, we're going to say any electric field to the right is positive and any electric field to the left is negative, independent of whether or not these values were positive or negative in our calculation for electric field up here. So now when solving for the total electric field down here, we're going to plug in the magnitude of our electric fields, and we're going to plug in for the signs, not the signs that we found when we calculated the electric fields. We're going to plug in signs that are consistent with their directions, and we're going to say to the right is positive and left is negative. That means this electric field, which is to the right, is going to be positive. This electric field is acting to the left, so we're going to put that in as negative. And last, there's this electric field, which is acting to the right, so that's actually going to stay positive. Now I know this is shown as negative here, but realize that negative was telling us attraction versus repulsion. It was not telling us about direction, which is what we need to worry about when adding up our individual electric fields. And we find the total electric field from these three charges is negative. That is to say, it's acting to the left. So I hope you found this useful in solving for the direction of the electric field from multiple charges. And on that note, that's all for now.